Please start. The floor is yours.
Great. Well, thanks everyone for joining. I'm Michael Thoreau. I'm a master's student at NYU. Last August, I'm going to tell a bit of a story here. Last August, I was part of a group of volunteers who assisted in a search and rescue operation for a missing paragliding pilot. He was missing in the remote mountains of Nevada, very challenging terrain, and it was a very large search area. Today, I'm going to talk a little bit about our approach to this problem, how and potentially how our findings might affect future search and rescue. So pictured here in the middle is the person who actually went missing. His name is James Johnson. He is a New Zealander, so he affectionately goes by the name of Kiwi. That's how I'll refer to him for the rest of the talk. So I want to tell the story a little bit because I want to establish essentially what the problem statement is, and then we're going to talk about maybe some solutions. So we were a group of volunteers who didn't know this person, but was brought into the operation by people reaching out, as they say here. And we had a couple of data scientists, some people who had expertise in satellite imagery and geoinformation systems. So, you know, we had a hammer and we were looking for a nail here a little bit. So I'll explain a little bit about the problem. So this slide here covers about 120 kilometers across. This is a very large area. And what we knew he had a satellite beacon. So we knew his last known position. And we knew approximately his direction of flight. We knew where he was supposed to be going. Highlighted in blue here is this, what was one of the larger search areas we covered. And this is around 8,000 to 9,000 square kilometers. So a square kilometer itself is very big, but 8,000 of them, this is really an incredibly large area to try and search for a missing person in. So I'll go back. What the object we were really looking for here is we weren't going to be searching for the person, we were going to be searching for the paragliding wing. This is a larger thing. You know, it can be up to 2 meters by 40 meters across, depending on how it may be landed or was spread out on the ground. So this is really the target we were looking for. And I would add that we think this research can also apply to things like missing light aircraft, small surface vessels, tents, vehicles, these kinds of things. So on the next slide, I'm going to zoom into this box here because this is where his paragliding wing, or that looks like a parachute, was found and where the search began. So this whole slide is approximately 35 kilometers across. We show his last known position, and we show the initial search area. Now, when we joined this project, the initial search area was being searched by air and ground resources. I think it was the National Guard and the sheriffs. It was the government agencies who were doing that. At some point during the search, which lasted 2 to 3 weeks, they gave up their search because they were only searching this initial area, and we continued with private resources being private helicopters, fixed-wing aircraft, and dedicated volunteer teams. So what I've also highlighted here is I've also shown, not to scale, for the next slide, the location of where the wing was found. And we're going to zoom into that now. So I want to show how the problem was kind of solved, and then I'll show some more things around that. So this is the wing as seen in a 500 meter by 500 meter satellite image. So I don't know if you can see it here, but I zoom in here, and what you can see is this is essentially a parachute, but in the satellite imagery, even though it's really high resolution satellite imagery, to be precise, it's 0.5 meter pixel resolution, is actually only a few pixels across. So essentially the problem statement here that we tried to solve at the time in a very small amount of time was, how do we find something that looks like this? And by the way, this is what the wing looked like on the ground when it was found. How do we find something that looks like this here? And I think this is obviously quite a difficult problem. So we attempted to solve this, and we had a few things up our sleeve. So we had this guy. Turned out he was quite a character, and he knew a lot of people in Silicon Valley, and those people had a lot of friends. And so through connections, in a really ad hoc manner, we were actually able to get access to a lot of really high resolution satellite imagery donated by a number of companies. The next tool we used, which I think is where this gets a little bit interesting, is we took a modern machine learning tool, which I'll talk about, and we applied it directly as part of our human-in-the-loop pipeline for searching these images. And the next thing we had was crowdsourcing. We reached out to the free flight and the paragliding and the flying communities, and it turned out there was actually a lot of people who really wanted to help with this search, but the problem is they just didn't have the tools to do it. So what we did is we gave them the tools, and we actually had 500 volunteers, 500 pairs of eyes on this satellite data, which meant over the course of 2 to 3 weeks, we were actually able to search around 10,000 square kilometers or more. I think it was a little more. So I'm going to talk about a little bit about our pipeline here. So in essence, the goal of what we were trying to do is, and we were connected to the ground and air search teams. We had this pipeline here where the input would be satellite data. And for this research, we're just restricting ourselves to purely satellite data here. High resolution, high availability satellite data from these modern constellations that have been launched in the last 10, 15 years. This is really a huge technological advance for us. So our input was satellite data. Our output was objects of interest that we would send to the search teams. So we'd say, hey, we've seen this on the satellite data. There's a lot of processing behind the scenes there, a lot of ranking of objects, a lot of human intelligence applied. But really the end goal is we're saying, hey, we want you to go investigate this potential object because we think this could be the missing paragliding wing. So this is, I think the first challenge here was actually getting the data. This guy was really lucky. Because he had a lot of friends, as I said, and so we were, through an ad hoc way of sending emails, making phone calls, we were able to get a lot of data. I don't want to think about how much it would have cost from these 3 companies. We're great debt to them: Planet Labs, Airbus Defence and Space, and Maxar Technologies. They were really good. The data they gave us actually forms the dataset that we're releasing today. However, I think this is a challenge. This guy was lucky because he had a lot of connections. However, I don't think other people have the same benefits. In fact, we've been contacted by 5 or 6 groups since this, saying, hey, we heard about this, we know of this person who's missing, can you help? And honestly, we've had to say no, because you just can't really get access to the data. I mean, it's just really just phone calls. And what I would suggest is, what I would really like to see, I'm not saying they should necessarily do this, but what would be good for them and good for everyone would be if they came together and collaborated on maybe a single platform where a group with a humanitarian request can put in a request, and then it can be fielded by one of these companies from a single location, rather than being an ad hoc process. Because I think that's bad for them. You know, it's just people emailing them, and it's bad for everyone in general, especially if you're lost. So once we have the data, the first thing we have to do is we have to find potential objects. And we also have to provide some kind of coverage. We have to say, hey, we had a pair of human eyes, or maybe in the future, an object detector from deep learning. We had a pair of human eyes look at every square meter of this data, and we can say, well, we didn't see this person here. We didn't see Kiwi here. So what we did is we tiled out our imagery. And at some point, we had like 30,000 tiles, 500 meters by 500 meters. You can see one here. We uploaded it to off-the-shelf bounding box labeling system. In this case, we used Amazon SageMaker. You may have heard of this because this is a service you can use where you can pay people to label your data. We briefly tried that. We worked out the performance was not going to be very good for us, but the volunteers we had were we were able to enroll 500 of them and get them onto the system, and they were actually able to do the labeling based on some examples. The examples we gave were objects we had seen on the ground that we had also seen from space, and we gave the pair of images, and we said, hey, look for things like this, please. So that was essentially the first pass. That was providing coverage and finding potential objects of interest. However, seeing 1 or 2 maybe detections per or labels per tile and sending all those to the ground team would not be very effective. This is just too many. So what we did is, and this was a colleague of mine, Chris Galley, full credit to him, he created this web app. Essentially, we have post-crash data, which is the satellite data that we were gifted, and reference data, which is from aerial or satellite imagery, And the job was to look at these images and say, hey, this object was not here previously, because if it was already there, then we don't have to worry about it. You might be thinking, well, what if we don't have the aerial imagery? Or what if we don't have high-res satellite imagery? Well, I would argue that, and this is my opinion, that the reference imagery doesn't actually have to be as high resolution, because I think in the post-crash imagery, you're looking for detail. In the reference imagery, you're really doing a comparison to see if the object is still there. So given that, we had humans, and this was a significant portion of our team, but not all of them, of the volunteers. We had humans looking at this, saying, "Hey, this object looks really interesting. That's being flagged. Let's prioritize this." And we had obviously like spreadsheets of data. Thousands of objects were ranking, and the highest ranked ones each day were searched by the team. So the last part of the pipeline, this is the output. We send an object of interest to the search teams, and then they did either a ground or aerial search. I think this applies to most search and rescue missions. Here in this image, we're showing only half of the density. I took off half the density of the air tracks that were taken. Huge area. I can tell you that the actual location for the wing was flown over multiple times and not sighted. On the right, unfortunately, this is the ground track. For once we found the wing, we actually went and unfortunately found Kiwi's body. He had died, unfortunately. I took it off the map for this purpose. But yeah, this is just an example of the ground tracks. And this is really a challenge for another day. There was a lot of use of drones and aerial and other things, but really we're not focused on that aspect. How they do the search, that's up to them essentially. So after the dust had settled and everything was over, I looked at the annotations we had, and these were bounding box annotations, and I thought, well, it would be silly just to throw these away. It'd be better to release these to the community. So we have approximately 2,500 images. More details are in the paper. 4,200 annotations. You can see some of the labeled objects here. I would argue that there is some noise in the labels. For example, I wouldn't have labeled this, but I think this image is actually really interesting. That could be something. I think this might have been a fallen tree, in fact. These are randomly sampled. So yeah, more details in the paper. There were some of the satellite imagery had maybe 4 or 8 channels. So we actually only took RGB for this case, but maybe that could be for future work. So as a byproduct of the search, from the humans looking at all the data, we created the data set. So the next logical thing is, well, I've got a data set of bounding boxes, I'm going to train an object detector. So we did that, and we showed it was quite effective. But really, I want to talk about how this could be useful for the search. So you might be thinking, well, did you find the guy using the satellite imagery? And the answer is no. And I'll go back because I'll explain what happened. Someone was actually driving along this road, and they saw the wing, as it was on the ground, kind of flapping in the breeze. And so they reported that, and I immediately found out the location and went, hey, how did we not find this with our really complex system? It turned out because we were trying to do full coverage and we were randomly sampling which images, and the image ordering was random, this was going to be in one of the last 5% of total images to be searched. We just got a little bit unlucky with the random numbers there. I'm confident though, looking at the image, we would have found it eventually, because I think it would have been labeled, and then it would have been flagged, and it would have been investigated eventually. So yeah, that's for me a proof of concept. So why use deep learning? So I would argue that in the finding object stage, and anecdotally, our volunteers were not slow, but definitely not fast, and they got very tired looking at every part of this image and making sure they don't miss anything. I would argue that, especially with a high sensitivity, an object detector can do a lot of that first pass for you. I think humans generally are better at a verification task than they are a coverage task. So I think a human could look at this and say, oh yes, this is nothing, that's terrain. Oh, but that's interesting, we'll keep that, and then clear some out essentially. So I think we could have gotten really much faster coverage here. The problem is we labeled essentially all the data and then used all that data for training. What I didn't investigate here, and it's not in the paper, was how much training data is actually required. I think there's a lot of opportunity here for online learning and few-shot learning to be more sample efficient here, but I didn't really investigate that. But I think there's an opportunity where humans would start by labeling, then we do few-shot learning perhaps, and then do kind of like a bootstrapping approach to improve the speed of coverage here. So that's how I think deep learning could be used in the pipeline. And yeah. So just for some results, so because it wasn't covered actually, the paragliding wing didn't actually feature in the train, validation, or test set. However, our best object detector was able to detect it with a 95% probability. And so I think that's, for me, that's kind of reasonable. Now, there's something else I wanted to highlight here. So what we've plotted here and we tested 3 different feature extractors inside FastRCN. Also, I should mention that the dataset is available on GitHub. The labels are in COCO format. There's examples for how to train FastRCN inside Facebook's Detector 2. So people can go ahead and do that if they like. Really, this is not going to be my core research going forward at the moment. So I just wanted to make it so someone could pick it up if they are interested. So I want to look at this because if you're talking to like a ground or air search team, a question I think you would never find yourself asking is, what kind of precision can you tolerate? I just don't think that's realistic. I think more realistic is we could say, how many detections per square kilometer, given the amount of data you have, can you tolerate given the human resources that you currently have? So what we've done here is we've plotted detections per square kilometer against recall. However, I wouldn't want to just say, oh, well, let's pick 20 detections per square kilometer as the upper limit and say, what's the recall of each of these? Sure, that gives you a number, but I think one of these goes down more linearly, one of these has a drop-off, so there's a little bit of difference there. So I had an idea for a metric which was maybe, for this application, an alternative to mean average precision. So I'll talk about that now. So, and this is not, I'm going to say this is not really a strong claim. This is just an idea I had that I documented and used in this case. I think more research is probably needed to say, hey, for these applications, this is definitely better. But what I did was I thought, hey, for our application, about 20 detections per square kilometer was approximately the maximum you would want to look at downstream. Sure, you might start with the highest confidence ones, but then as you come down, maybe you stop at some point. But what I wanted to look at was, well, let's not look at a single recall point. Let's look at the average recall for confidence thresholds above what would give 20 detections per square kilometer. So I called that the ADR20, or the average recall below 20 detections per square kilometer. Obviously, I would be open to new names. I don't think it's a great name. So using this quantitative metric, I compared the 3 object detectors, and sure enough, the feature extractor which was highest in the graph most of the time had the highest ARD20 score. So I think that's potentially useful. I think it's a potentially useful metric here. And just as before I sum up, so we talked about the whole pipeline. I just wanted to share, because I think this is interesting. These were actually some of the objects that we investigated based on the satellite imagery. And in my view, if we can find this, we can find other things like part of a light aircraft wing or a parachute, things of this nature. So you can see we found some signs here, some weather balloons. This is what the weather balloon looked like from space when it was hanging up in a tree. Small slab of concrete, this tarpaulin here with the satellite image here as well. And for me, I think this was kind of a test of a system that didn't really exist yet, but now it does exist. It exists in concept at least. I think that's maybe a little bit of momentum, hopefully, for making this kind of crowdsourced search and rescue a possibility in the future. So hopeful about that. And obviously a big thanks to our data donors, so Planet Labs, Airbus Defence and Space, Maxar Technologies, and obviously the 500 volunteers and air and ground search teams. And with that, hopefully I was in time, and I'll take any questions.
Thank you for a nice presentation. It is a really noble cause that you have attacked here. So I'm opening the floor for questions. There is one in the chat. So can you see the chat, or should I read it?
No. Can you read it, please? Sorry.
Okay, it's from Nai Dosai. It says, as mentioned in your presentation, the use of drones would be much easier to find the objects when the point of object interest is smaller. Don't you think satellite imagery will be much more complicated when you're looking for smaller objects? So
yeah, definitely.
Comments on drones with satellite imagery.
Yeah, definitely. And I think what would be the core future research for this is not, so why use satellite imagery when the objects end up being so small? The fact is that you can, if I had the money to do it, or the humanitarian need and the company was willing, I could say, hey, middle of Australia, middle of nowhere, I'm going to pretend, which is where I'm from, I'm going to pretend someone went missing and say, hey, can I get a really high-res image of that? Can I have that today, by the way? Where I would argue that deploying an aircraft or a drone to that area is actually much smaller, and that can be important maybe for ocean searches. We end up using these drift models. So there was like MH370. There was also this. There was a boat that went missing right after we finished this search. And in fact, we reached out to the Australian government because there were some Australians on board. They essentially said, no, we're not going to support this at all. We're going to leave it to the Japanese Coast Guard. In fact, getting data, it was kind of an interesting story. Getting data for that was a little bit complicated, as the area in question was the South China Sea. The satellite imagery companies weren't so keen for some reason. But I would argue that we can have higher availability and faster responses. But I think for future research, I would really like to see how adding more sensors, well, drones obviously have a lot of sensors, more sensors to aircraft and drones, and using them in a similar kind of pipeline would actually be interesting. So say you do kind of like doing aerial imaging or an aerial survey, you take that data and you feed it into this pipeline in lieu of satellite imagery, and you just do a higher resolution alternative. It turns out if you had a GoPro on an aircraft at about 4,000 feet, that gives you a 0.5 megapixel pitch with a certain wide angle lens, I think. Just a back of the envelope calculation I did. But you could obviously go lower, use different lenses, and I think there could be really something in that. The way we revisit and consider data, given context of reference data, as well as having multiple sets of human eyes on it, maybe introducing deep learning. So I think, yeah, it's a really good point. I would like to see drones accomplish this.